Okay, so how is everyone today? All right. So now we have an interesting topic. All right, so we've got to review. We've got the exponential model. Okay, so then the exponential model differential equation is this: dp dt is kp. And so conceptually, I want you to be able to read this equation sort of to have an intuitive idea of what it's saying. It's saying that the rate of change of the population is proportional to the current size of that population. Okay, so now there's sort of two cases. Well, there's three cases, but one of the cases is just boring. So if k is negative, that's one possibility. If k is 0, that's one possibility. And if k is positive, that's the last possibility. So if k is negative, and if we're talking about a population of real objects like rabbits or something, to where it doesn't make sense for there to be negative rabbits. So if k is negative, then kp would be negative, right? Kp would be negative. And that would be saying that the rate of change of the population is negative. So what does that mean about the population? It's decreasing. Another way to think about it is that P, the population, this could be a population of uranium atoms. Okay, so then of course you can't have, negative uranium atoms. So in that case, K is negative, and that represents the decay of uranium atoms. Okay, so the picture in that case looks like this. That the population will decay. And then if you go backwards in time, it must have been like that. K equal to 0, I'm saying, is a boring case. So why am I saying that? It's not that there's no population. The population could be positive. Yeah, the population's just not changing, right? So yeah, so it would be saying that dp dt is 0. And then as a consequence of the mean value theorem, that means that p must be a constant. All right, so that one's kind of boring. Positive. In this case, again, if p is a positive thing, and furthermore, if k is a positive constant, then kp is positive. So that means that it's saying that the population growth is positive, which means, the rate of change of the population is positive, so it must be growing. And furthermore, because it's in proportion to its current size, it must be growing exponentially. And if you were to project backwards in time, like that. All right. Of course, the solution to the exponential model, the solution is going to be p is equal to some number, a, exponential kt. And then in the specific case that you arrange matters, that you happen to know the population at time 0. So if you arrange things so that things occur at time 0, then that can be P0. So if you know that P evaluated at 0 is P0, then the model is P is equal to P0 multiplied by exponential KT. All right. So now, here's a very similar one. What if we have it could be a salt tank where we're pouring in salty water, like that one that we did, or it could be a bathtub where we're pouring in new water of a constant temperature, or it could be that we've got some object that's red hot and it's in a room that's at room temperature and it's cooling down, or we've got a very cold object in a room that's at room temperature and it's warming up. So I don't know, the book doesn't have a name for this one, so I'll just call it the forced model. It's very similar to the exponential model, and it is this, that dp dt is k multiplied by I'll say e minus p. So what this is, the way to interpret this, is that it's saying that the rate of change of the population is, okay, so because of the k, it'll be proportional to and it's going to be proportional to this. Now, the way that we're going to interpret these is, of course, this is the current population, and this is going to be, we'll interpret that as the environment. Now, that could be something like, well, if you've got a bathtub and it's full of cold water, and you want it to become warm, then turn on the warm water at the temperature that you want, and arrange the drain plug so that water is flowing out of the tub at the same rate that water is flowing into the tub, and mix it all up. Then after a little bit of time, the tub water will be the same temperature as whatever's coming out of the tap. So that would be the environmental forcing. So in this case, we're always going to consider the case that k is positive. And in this case, it's going to look like this. So we solved one that is more or less just like this with the salt. So this will be when the population is exactly equal to the environment, and if the population starts out lower than the environmental forcing, then you'll increase to the forcing factor like this. So we saw that when we were doing the salt, right? It was the initial salt bath was less than the initial salt concentration was less than what was coming out of the tap. If it were the case that the tank had a much higher concentration of salt, and we were pouring in relatively less salty water, then the concentration in the tank would decrease. To whatever's coming out of the tap. So what I want you to observe is that qualitatively what this equation is saying is that the rate of change of whatever it is you're tracking is proportional to the difference between the environmental force and the current value. So, which is to say that if, for example, if you interpret this as temperature, and that as room temperature, and if the current temperature is less than room temperature, then the object will heat up, right? So if P is too low, that means that E minus P will be positive, K is positive, so the change in temperature will be positive. So we'll warm up. Whereas if you're too hot, which is to say if P is more than E, then that difference will be negative, so that product will be negative, so the change in the temperature will, the temperature will decrease, like this. Very good. Then, besides those, we also talked about the logistic model. Now, in this case, the statement is that the rate of change of the population is proportional to, in the first place, the current population. So it's got to be proportional to the current population. And moreover, we also want it to be proportional to this, 1 minus P over M. Now, in this case, M is, you might conceptually understand it to mean the carrying capacity. Like how many individuals can the environment support? So consider, if, ignoring that one for a moment, which is going to be a positive value, so you could think of this like the number of human beings. If the carrying capacity of the Earth is 30 billion, and the current population is 7.5 billion, then this ratio will be more or less than 1? It will be less than 1. So that 1 minus that will be something positive. So as a result, what that's saying, the meaning of this factor, it's saying that if the current population is less than the carrying capacity, the population should increase, should go up. Right. Because all of that will be positive, assuming a positive K. All right. Well, what if what if there was some environmental catastrophe, like I don't know, like if suddenly we lost half of all of our farmland for whatever reason you care to imagine. Okay, then suddenly the carrying capacity of the Earth maybe it drops to 5 billion, and there's 7.5 billion of us. But we don't have enough food for everyone anymore. So then that would be 7.5 over 5, and so that ratio would be more or less than 1. It'd be more than 1. So that 1 minus that number would be negative. So that would be saying that the rate of change of the population would be negative, so that we should decrease to the carrying capacity. Of course, that's a polite way to say that massive die-offs, right? that's what that means. So the logistic model, when you plot it, looks somewhat like the forced model. Somewhat like the forced model, in that if you ever start more than the carrying capacity, you must decrease to the carrying capacity. If you start less than the carrying capacity, you will increase to the carrying capacity. So far is seems just like the forced model. But the distinction is that this extra factor causes that behavior like this, that if you start much less than the carrying capacity, then at first you'll increase in a manner that kind of looks exponential, and once you get past that point, you'll go through a point of inflection and then increase to the carrying capacity. Whereas the forced model, all of them will increase exponentially to the carrying capacity. Good. So now, here's the deal: is that this is a little bit too simple, of a model, and we want to have something more interesting. So you can imagine, what if somehow, we took a nice forest and we deleted all of the rabbits and all of the wolves, okay, all the predators and all the grazing animals, and then we introduced some rabbits, right? So then the rabbits would be limited only by how much food the forest can produce, right? Because there'd be no predators attacking them. So in that case, the correct model for rabbits, assuming you delete all the wolves and cats and whatever, would be logistic. So you introduce that first pair of rabbits, their population will grow quite rapidly at first, and then they go through this point of inflection, and that's more or less where they're starting to heavily compete with each other. And then it will still slowly increase to the carrying capacity. Yes?
So that process of competing with each other, the point of inflection, that happens to, are there limitations?
I don't understand.
For what kind of population it happens, or
Well, it just depends on these constants, on these things, like what is the actual carrying capacity, and how do you interpret that constant? That might mean something like the interpretation of that constant might mean something like you can only support in 1 acre maybe 20 rabbits. That's kind of how you could interpret that.
So based on that, we'll have to know if it is logistical or the forest. When they examine, the test.
Oh, okay. So as for a question,
Yeah.
Well, so this one, it's that this is the kind of model that you use if it's going to be exponential, like radioactive decay or unbounded population growth. So that's this one. This is something like you want to know how fast does something move to room temperature. So that's the meaning of this one. And this is it's probably the best idea is rabbits, but in the presence of no predators. Okay, if you start with very few rabbits, population increases quickly until more or less they're competing with them with each other, and then that. All right, but it's not realistic. It's not realistic because in the end there really are actually wolves, right? There really are actually cats and what have you that eat rabbits. Okay, so now what we want to do is consider that we've got a predator, like a wolf. I'll just say wolf from now on, and a prey animal, and I'll just say rabbit. So the rabbits somehow feed off the environment, off the forest, and the wolves can't eat the forest stuff. They have to eat the rabbits, right? So if it ever comes to pass that there's no wolves, then wolves are not going to spontaneously generate, right? We're not going to poof, no wolves will poof into existence. And if it ever comes to pass that there's no rabbits, then what should happen to the wolves? They should die. And the population of wolves that can be supported should somehow be in proportion to the number of rabbits, which means that if we've got lots of rabbits everywhere, we should be able to have lots of wolves. But there's sort of a feedback going on, and that is that if you've got a whole forest full of rabbits, and they're all doing their thing, and then you introduce a pair of wolves, those wolves should do really great for a while. But after a few generations, and you're starting to have lots and lots and lots and lots of wolves, well, the number of rabbits should be going down a little bit, okay? And there's going to be, we have to find some kind of equilibrium. Okay. So the name for this kind of idea is called the predator-prey model. So that's kind of what it's called in engineering and science circles. But when you get into math circles, it's named after the folks who studied it first. They're called the Lotka-Volterra equations. model. All right, so we'll say this, that R, this represents the number of rabbits, and W, the number of wolves. And so we need to think, how will the population of rabbits change in time? So dRdt is, well, in the first place, if there were no wolves, then the number of rabbits should increase in proportion to the number of rabbits, right? More adult rabbits means more baby rabbits. Okay, so we should have something that looks like KR. I want to make sure I use the same constant as the book. Okay, good. So now, in addition to that, besides that, so we'll want this K to be positive, right? Meaning that adult rabbits make rabbits, they don't destroy rabbits. But we should also, if we have some number of wolves, then the wolves should be taking rabbits out of the population. So the way that we'll encode that, we'll say also the rate of change in the number of rabbits should be proportional to. So again, that's just a proportionality constant. And because I wrote subtract, that means that this A is going to be positive. If I wrote add, then the A would need to be negative. So the number of rabbits that needs to be taken away, in the first place, has to be proportional to the number of wolves, right? Because, well, the more wolves you have, the more mouths to feed, right? But furthermore, then, you also have to consider, even if there's lots and lots of wolves, if there's not very many rabbits, then there won't be very many opportunities for a wolf to find a rabbit, right? And if there's lots and lots of rabbits, then there should be the opportunity for a wolf to find a rabbit should be relatively high. So if we're taking rabbits out of the population, not only should it be proportional to the number of wolves, but it should also be proportional to the number of rabbits. Okay, so this is how the number of rabbits should change as a function of time. All right, let's think about how the wolves should change. So dW dt. So what do you think? Sorry? Instead of what minus, it's a plus. All right. So then, more or less, you can think like, there's some, if you were to do an ecological study, you could find out that perhaps that for a given female wolf, maybe it's the case that it takes exactly 35 rabbits to have one litter, to go through one pregnancy, and successfully bring a litter into existence. So as a result, we'll need something that's proportional to the number of wolves, and the end result is going to be this. So we'll have to have plus B R W. So what that means is that the number of new wolves coming into the population, has to be proportional somehow to the number of rabbits and the number of wolves. Okay, so it's got to be proportional to the number of wolves because you can't make baby wolves without adult wolves, and it's got to be proportional to the number of rabbits because you can't successfully have a go through a pregnancy without I don't know, maybe 35 rabbits. I have no idea. Maybe it's 300 rabbits. I really don't have any idea. But the way that new wolves come into existence must be this way. Now, in addition to that, we have to have some way to express how the wolves go out of existence. So they go out of existence, either through death or leaving the forest, or killing each other one way or another. So we'll represent that as just a minus r multiplied by w. So somehow what we're saying is that the number of wolves that die is proportional to the number of wolves that there currently are. Okay. So now we have two differential equations. And notice that the solution to this differential equation should be r of t, some function r of t, and the solution to that one should be a different function, w of t. So really, this is actually a system of differential equations. And what we want is we want to find two functions r of t and w of t. Two of them which satisfy each of those. All right. Interesting. So now, in this class, we don't really try to actually find solutions, like analytically. Like it's not going to be the case that you're going to say, as a result, r is equal to what have you, and w is equal to what have you. Rather, the point is that you should be able to look at an example of these equations and come up with some qualitative ideas about them. All right. So here's so that's the idea, and now I need to bring in one more thing, and that is that of course there's this thing called the chain rule, ddx of f of g of x. The chain rule tells you how to compute the derivative of a composition. So the chain rule is saying that well, you're going to have to differentiate f, and you're going to have to differentiate g. And then once you've differentiated them both, how do you combine them? With a multiplication, right? And then the question is that the question remains is that where are you supposed to evaluate each one? So where is g evaluated? At x, right? And where's g prime evaluated? I mean, should have said. And where is f prime evaluated? At g of x. Right, so then you differentiate both functions and you have to multiply them together. This one is evaluated at x, that one evaluated at g of x. Okay, but if we use the Leibniz notation, that is like dy over dx, if we write that instead, if we write y is f of x, no, if we say y is f of u, and u is g of x, then writing this in Leibniz notation, it's saying that, well, dy dx, so notably, y is not expressed as a function of x. Rather, it's expressed as a function of u. So the question is that if you've got a function that's expressed in terms of something u, and you're differentiating it with respect to something else, x, then the way that it works is that, well, we should get what?
dx or dx.
Well, you first differentiate y with respect to u, so that'd be dy du. So differentiate that with respect to u. And then for the chain rule, what?
du over x.
du
Or dx.
dx. Now, again, these things that we have written here, they're dy and dx and things like that. They're not numbers, and they're not functions. They're actually something else. Depending on the context, they're either called a differential form or a measure. But what I want you to observe is that this notation is suggestive if we suspend our knowledge that those aren't really numbers, and therefore those aren't really fractions. If we just temporarily imagine them to be fractions and we made a cancellation, what would cancel? The du's would cancel. And what would remain? Amazing, right? So that's the reason for that notation. Now, be very careful, it's a little bit slippery. Now, that being the case, so that's the chain rule. And we also have something called the implicit. No, not the implicit. In this class, it's called the inverse function theorem. Which is to say that what if you have a function f? What if you have a function f and it's invertible? And furthermore, for this function f, you know its derivative. Then what's the derivative of the inverse function? Right? So it's asking a question like, well, consider two functions that are inverse to each other, like log and exponential. Suppose you know exponential, you know everything there is to know about it, and you know how to compute its derivative. Then the question is, well, using that information, how can you compute the derivative of the inverse of exponential? How can you compute the derivative of logarithm? Well, it's saying this. So suppose we have y is f of x. Suppose that we have y as f of x. And suppose further that we're able to invert this equation so that we can have f inverse of y is x. So we're able to get f on both sides. So that could be something like squaring and square root, log and exponential, what have you. So the question is that, all right, how do we calculate the derivative of the inverse function at y? How do you calculate it? Sorry? Well, okay, then let's just do it. What is it? Yeah? Very good. So it's 1 over the original function, the derivative of the original function, evaluated at x. Huh, that's interesting. So in the Leibniz notation, that's saying that, amazingly, that dy dx, in fact, that's not the one that we want. Rather, we want dx dy. Dx dy is 1 over dy dx. So again, it kind of looks like a fraction. But you have to be very careful because look at the inverse function. Where is the inverse function's derivative being evaluated? At y, right? And where is this one being evaluated? At x. So the slipperiness and danger of this notation is that you might lose track that, oh, this is a function being evaluated at one place, and that's a different function being evaluated at a different place. But that being said now, that being said, we can combine those. Combine the chain rule and inverse function theorem to do the following. So what we're saying is that suppose that we have dr dt. Suppose that we have these, dr dt and dw dt. suppose we have those, then we can get something else. So now, pardon me, as these are written, if you were to multiply them together, then there wouldn't be any cancellation, right? There wouldn't be any cancellation. But you know, if we imagine them to be, you know, imagining them to be fractions, if we computed the reciprocal of one of them and then multiplied them together, then there'd be some cancellation, right? What would cancel? The dt's would cancel. So what I want you to observe is that, well, because we have these, and because we have the inverse function theorem, and because we have, say, dr dt, then we can just as well calculate dt dr. And we can obtain the following, that dt dr multiplied by dw dt should be what, according to the chain rule? dw dr. Interesting. So what the way to interpret this is that it's saying how fast, well, it's saying what is the rate of change of the number of wolves with respect to the number of rabbits. Interesting. So let's consider such a problem. Good. So suppose suppose that we have given the predator-prey model with these constants, with k is 0.08, a is 0.001, r is 0.02, and b is 0.4 zeros and a 2. So given the predator-prey model with those particular parameters, we want to find, in the first place, find the constant solutions. All right. So let's try and understand what could possibly be meant by that. What is meant by that is that somehow we've got this population of wolves and rabbits, and it's come to pass that the number of wolves is not increasing, and or decreasing, and the number of rabbits is not increasing or decreasing. Now that doesn't mean no wolves are dying, and that doesn't mean no wolves are being born. Rather, it just means that the number of wolves dying and the number of wolves being born is the same. And similar for rabbits. There's rabbits coming into existence, there's rabbits dying, wolves are eating the rabbits, you know, stuff's happening. But the population is not moving. So to find the constant solutions, what must be true?
Both dRdt and dwdt must be 0.
Right. So so let's calculate it out. So copying down the model from the previous page, it was dr dt is kr, and then subtract a r w, and dw dt is brw minus rw, yeah. So find the constant solutions. So how do we do it? So what do we need to do? Right. So let's solve the equation, the system of equations, dr dt, dw, dt equal to 0. So it's a system. They have to both be 0. All right. So plugging all those parameters in, so we would have 0.08 r minus 0.001 rw equal to 0. And we'd also have that crazy number there. 0.402 RW minus 0.02 W is equal to 0. All right. So we want both of these equations to be 0 at the same time. All right. So there's some trivial solutions. So what I mean is that solutions that in some sense aren't interesting. So because of the way this is structured, we could factor out an r, right? Okay. So in order for that one to be true, so from equation 1, and just working on it for a moment, we could factor out an r and obtain that r multiplied by all of that, 0.08, and then minus 0.001 w equal to 0. So now we've got the product of those two things is 0. So that means that one of those things has to be 0. So there's two possibilities from there. The equation splits into r is 0, or I'll say this one is equal to that one. So would someone please explain that? Why is that a constant solution?
Because r is in everything, because you multiply r by.
No, I mean in the physical problem.
Oh, rabbits.
Yeah, it's saying that, well, what if you have a forest and there's no rabbits in it? Then there's not going to be any rabbits, right? they're not going to spontaneously generate. Okay. What we haven't gotten there yet, but what do you suppose will be a consequence in the case that r is 0? W is probably going to have to be 0 too, right? Because if the rabbits are the only food source of the wolves, then you can't have any wolves either. All right, so then r is 0, or using my calculator there, we'd want to multiply by 1,000. So what's that? Multiply by 1,000? No, multiply by, yeah, 1,000. So W would be 1, 2, 3, 80. Did I do that right? Yeah. So, or 80 wolves. Okay, then that's what equation 1 is saying. Now, what is equation 2 saying? So similarly, we could factor out a W, right? So factor out a W. All right. So again, that's the product of two things has to be 0. So either the first factor is 0 or the second factor is 0. So that would be W is 0 or what? I can't do that in my head. Well, I probably could, but I won't risk it.
That should be our first one.
1,000, yeah. Good, thank you. Or R is 1,000. All right, so can you interpret that for us? What does that mean?
There's 1,000 rabbits. There's 8.
Very good. So, you know, the constant solutions must include these. So now, the next question we want to address.
Sir,
Yes?
does that mean that they're in equilibrium, so the population is not going to grow if there's 80 wolves and 1,000 rabbits? They're just equal?
Right. So what that would mean is that you know, it might be better to think of this like as in millions. So like there's 1,000 millions rabbits and 80 millions wolves, so that there's a lot of them, and you don't have to think so much about thinking one wolf is important. What it means is that the wolves are dying and being born, but the population is over time is not going up or down. So basically, we'll be stuck at about 80 wolves, or 80 million, and 1,000 rabbits, or 1,000 million rabbits. Okay, good. So now the next, concerning that same model, the next thing we want to answer is let's find dWdr. So let's do that. So how do we do it? In this, you have to use the chain rule and the inverse. What am I trying to say? The inverse function theorem. Brain is not happy. So dWdr, according to the chain rule, will be what?
dw dt.
Mm-hmm.
dt over here.
dt dr. Like that. Now, according to the inverse function theorem, you know, we don't have the derivative of time with respect to the number of rabbits. And, you know, sort of arguably that doesn't really make a lot of sense physically, right? How does time change with the number of rabbits? But according to the inverse function theorem, we can still calculate this. How do we calculate it?
Inverse of dr dt.
Yeah. So this should be equal to dw dt multiplied by 1 over dr dt, like that. So copying that from the previous page, it's telling us that the model should look like this. So wolves are on the top there. So 0.402 RW minus 0.02 W divide by 0.08 R subtract 0.001 RW. So that's dWdr. So what that, you know, physically, if you to interpret that in terms of the story, that's telling you how the number of wolves change with respect to the number of rabbits. Now, you remember we made a slope field. Remember we took a thing and we plotted you know, little slopes all over the place. Now you could make a slope field for this. So what I'm going to do now is just sketch out more or less what the slope field looks like. This will be the number of rabbits. This will be the number of wolves. So we know that if ever it comes to pass that the number of rabbits is zero, the number of rabbits is 0, or the number of wolves is 0, then there's not going to be any change because the population will have become constant. Okay, but we also know from the previous item that there's an equilibrium point at how many wolves and how many rabbits? 80 and 1,000. So at 80 wolves and 1,000 rabbits, we've got a point. And if we ever get there, then we'll stay there. That will stay still. All right. So if we ever get more than 1,000 rabbits, then that means that the number of wolves can increase, right? Because there's going to be more to eat, and then the number of rabbits will decrease. So what's going to happen? We're basically out of time. What's going to happen is that the slope field is going to end up looking like this. You'll have orbits. That are going to end up orbiting around this point. Now, depending on the problem at hand, that you may in spiral down to that, like you may orbit in spiral down to it. So, what I mean is that if we ever got here, that many rabbits and that many wolves, then in time, what will happen is that you'll do this. And the final thing I want to say about this is that notice that this plot does not include time. It's only rabbits and wolves. Time was eliminated right here with the chain rule. So what I want you to see is that the number of rabbits as you go through that loop is oscillating. It's going up and down and up and down. And the number of wolves is also oscillating. Up and down and up and down. So depending on those constants A, B, K, and R, you might spiral to the equilibrium point, or you might just never reach that equilibrium point. Okay, have a nice weekend.